So we are starting to work on the sections in Chapter 6 that cover probability. And the first thing we want to do is talk a little bit about notation. Whenever we're talking about the probability of an event, a really easy way to notate that is to perhaps, call the event A, or you can call it whatever you want. But in a lot of these examples, we're going to refer to some event A. And my pen's not working. Here we go. And if we want to talk about the probability that event A happens, then we're just going to notate that P of A, P of course, for probability. And then we're going to either assign that probability some value or we'll calculate that probability somehow. But you'll see lots of notation in this chapter where we've got this P of A notation. It's very similar to function notation, which you should be familiar with. If you recall that from either Algebra 2 or Pre-Calculus, if you're in that class now, function notation looks something like f of x. So we're not saying that we're taking the function or some number f and multiplying it by x. It's just some function f that we're evaluating at the point f. Same thing with this probability notation. We're not multiplying p times a. We're taking finding the probability of some event a. We'll talk about this a little bit more in later sections, but I do want to quickly talk about some properties of probability. But before we get into that, let's just mention what probability is. You've probably heard of probability before. You've probably even spoken in terms of probabilities before. Probability is simply a measure of the likelihood that a certain random event is going to occur. So if we are measuring the likelihood of a certain event, that gives us some parameters for the value of that the probability can take on. The smallest possible value that a probability could have would be 0, meaning that the event never occurs. And the largest possible value for the probability of event, then of course, is 1, meaning that the event always occurs. It is impossible, there's no such thing as having a negative probability. There's also no such thing as having a probability greater than 1. If your probability was greater than 1, that would mean that this event is happening more than all the time, which just isn't very likely to occur. Something else we need to talk about is a little bit of terminology. First of all, sample space, that's just the set of all possibilities, all possible outcomes. So if you are tossing a coin, then the sample space contains 2 possible events, either getting a heads or a tail. If your event is rolling a die, then you have 6 possible outcomes, rolling the numbers 1 through 6. If you are drawing a card out of a deck of cards, the sample space contains 52 different elements because there are 52 different cards. Then the event is simply the outcome or some sort of set of outcomes from some sort of random phenomenon. And the word phenomenon makes it sound a little bit more fabulous and outstanding than it really is. But the event simply could be, suddenly can't spell. The event simply could be tossing your coin, rolling a die, etc. Just because it's a random phenomenon doesn't mean that it's any sort of crazy event. It could be something pretty mundane. So you do need to be comfortable using those 2 terms, sample space and event. When you are trying to figure out how many elements are in your sample space, a tree diagram can be a convenient way to determine all of the possible outcomes that reside within your sample space. Now, sometimes in some situations, it might be pretty easy to figure out what your sample space is. We've already mentioned if you toss a coin, the sample space is just coming up heads or coming up tails. There are only 2 elements in that sample space, so that's pretty simple. But what if you have a situation that's a little bit more complicated than just tossing a single coin? in your book, they give you an example where a coin is tossed and then a die is rolled, and they come up with all of the possibilities for that sample space. Just to give you another example, let's say that we toss 2 coins. So again, we can use a tree diagram to give us the overall sample space. So here's our starting point. If we're going to toss our first coin, of course, like we've already mentioned, there are only 2 possible outcomes. We could get heads or tails. But if we're going to then toss a second coin, that coin, of course, could come up heads or tails. And so we end up having a total of 4 possibilities if we toss 2 coins. We could get 2 heads in a row, we could get heads then tails, we could get tails then heads, or we could get 2 tails in a row. You can keep using these tree diagrams as your situation gets more and more complex. Let's say we toss 3 coins. Well then, of course, off of each of these branches we have another head or tail possibility. Heads or tails, heads or tails, heads or tails. And then you can just read down the tree what each branch of that tree represents. So this first branch would represent 3 heads all in a row. Then just below that it would represent having 2 heads and then 1 tail. And then the next one would be heads, tail, heads. And then head, tail, tail. And then we switch over to having a tail for the first one. Tails, heads, heads. Tails, head, tails. Tails, tails, head. And then all 3 tails in a row. So this leads us to the next idea, which is the multiplication principle. And just so I don't have to copy all that back down, I'm going to revert to the last slide for a second. The multiplication principle simply says that as you are calculating the total possible number of events in some sort of compound event, you simply multiply by each of the possibilities. So here in our example, we had sort of round 1 where we tossed the first coin and there were 2 possible outcomes, heads or tails. And then in round 2, when we tossed the second coin, there were 2 possible outcomes. And then in round 3, when we tossed the third coin, again, there were only 2 possibilities, heads or tails. And so if we multiply the total number of possibilities for each action, we get the total number of outcomes. So 2 times 2 times 2 is, of course, 8. And if you notice over here on the far right side of the slide, we have 1, 2, 3, 4, 5, 6, 7, 8 total possibilities in our sample space. And that's really all the multiplication principle says. Last thing I want to talk about for this video is the idea of sampling with and without replacement. And this is something that you're going to see somewhat regularly within this the rest of this chapter. And you just need to pay close attention to which situation you're dealing with. Really easy example of this would be to say, all right, let's say you've got a bag of marbles and you've got, I don't know, 5 blue marbles, and let's say you've got 4 red. And so you want to know what the probability is of drawing or pulling out a red marble. Well, on the first draw, that's pretty easy. You have 9 total marbles. So if you want to know the probability that you're going to draw out a red, well, there are 4 reds in the bag out of 9 possibilities. So the probability of drawing a red marble on the first draw is 4/9. Now this idea of replacement comes in where what you do next after you draw that first marble determines what's going to happen to the probabilities on subsequent draws. If you just put that red marble that you drew out of the bag back in, then of course on the second draw the probability of drawing a red isn't going to change. It's still going to be 4/9 because there are still 4 red marbles and 9 total marbles to choose from. However, if you did not replace the marble, I'm going to call this R prime, now there aren't 9 marbles in the bag anymore. There are only 8. And we're going to assume that our first draw was a red marble, so now there are only 3 to choose from. So now our probability of drawing a red on the second draw would be 3/8. And then, of course, if we continued to not replace that red marble, our probabilities would have to adjust for each subsequent draw. And that's really all there is to sampling with and without replacement. It's whether or not your whatever outcome you got on your first attempt, your first trial, do you throw that outcome back into the mix of things, or is that outcome totally removed from your possible sample space?